Please be seated. Good evening, ladies and gentlemen. It's indeed a privilege to have you here at this wonderful event tonight. We will be celebrating the inaugural lecture of Professor Aletta Prinsloo. All of the best. We're looking forward to your lecture a little bit later as well. I must say you've done a great achievement. We often just talk to the left-hand side of the house. Tonight we're going to talk to the right-hand side and the left-hand side of the house. So you've really done well. You've started off very good. Let me also acknowledge our Executive Dean of the Faculty of Science, Professor Deborah Meyer. We've already welcomed our inductee, Professor Herman Alberts, who will act as a respondent. It's wonderful having you back at the university again. Warm word of welcome to you as well. Senior leaders of the university, members of Senate and other academics, distinguished guests, ladies and gentlemen. It's indeed a privilege to have you all here with us tonight. So let me welcome you to this professorial inauguration of Professor Aletta Prinsloo. And as I do so, also allow me to wish a warm word of welcome to her loved ones. And I'm going to mention a few. Her husband, Richard. I know the colleagues are all sitting here. Daughter, Maria. Her father, Dolph. And in-laws, Anna and Joel. And I believe there's other family members as well. It's indeed a privilege to have you all here with us here tonight. It's a very special event for you as well. Also to other special guests and colleagues. This is indeed a proud and joyful yet a landmark moment for all of you, for Professor Prinsloo, and of course for all of us here at UJ, the faculty and higher education in South Africa and beyond. The inauguration of professors is a public ceremony in which newly appointed professors are inducted into office by the Vice-Chancellor, in this case the Acting Vice-Chancellor, and deliver their inaugural addresses. The ceremony has its roots in the medieval university and serves multiple purposes, and I'm going to highlight two of those purposes here tonight. Firstly, it's an expression of welcome and an entry for new professors joining the circle of colleagues who are already professors. And secondly, it provides a platform for the professors to display their expertise in the discipline and showcase their research. Today we gather to bear witness to the entry of Professor Prinsloo to the illustrious community of scholars at this university. It is a celebration of the contribution to the discipline and ultimately the related impact on society. Professors, Professor Prinsloo, provide the university with its identity, character, academic legitimacy and integrity. The inaugural lecture is a rite of passage following the confirmation of the appointment of the person as a professor. It stands out as a moment of pride for the incumbent, the family, fellow scholars, the university, and ultimately society. Recently, universities has been viewed as instrumentalist, serving the purpose of the economy or utilitarian in its purposes. I would hope that we can break out of these narrow conceptualizations and reflect on the university as contributing to the public good, with information that contributes to the broader needs and development of society. So, what do we define as the ideal role of a true intellectual? I would just like to highlight from Edward Said in an article on defiance and taking positions, his viewpoint on the ideal role of the true intellectual, and I quote, "One who commands a vast knowledge of his or her discipline, who is rigorous in the analysis of literature, who views being an intellectual as a vocation, the intellectual who considers it necessary to step into the public sphere and to speak truth to power, namely to question, interpret, and understand authority rather than consolidating it, to step out of the boundaries of the academy, to connect oneself, to affiliate oneself, to align oneself with an ongoing process or contest of some sort, perhaps with the aim of improving the lot of the oppressed, the intellectual who functions as a kind of public memory to recall what is forgotten or ignored, to make the connections that are otherwise hidden, and to provide alternatives for mistaken policies." Close quote. So, as we listen to you this evening, Professor Prinsloo, we must understand that this is one further step in your journey of being a professor. This is a journey which does not culminate once your lecture has been given here tonight, but actually as a new starting point in your journey going forward. So it's a self-reflective pause in your future journey, with a promise of more to enrich our minds and simultaneously contributing to the rich intellectual body of the work in your specific discipline. Let me now invite the Executive Dean, Professor Deborah Meyer, to introduce our inductee. Thank you very much, ladies and gentlemen.
Good evening, ladies and gentlemen. It is indeed a privilege to introduce you to Professor Aletta Prinsloo, who graduated with a BSc Ed with physics, chemistry, mathematics, and education as majors from the Rand Afrikaans University in 1991. As you know, the Rand Afrikaans University is one of the legacy institutions of the University of Johannesburg. Aletta completed her honors and master's degrees in the following 2 years at the same institution, after which she started working as a teacher. She enrolled for a PhD at RAU in 1995 and completed her degree in 1998 under the guidance of Professor Alberts and Professor Smith. The PhD research focused on the physical and magnetic properties of spin density wave chromium silicon and chromium gallium single crystals. While working on her PhD, she lectured at Vista University, Soweto campus, another legacy institution of the University of Johannesburg, and she did this from 1996 to 1998. Upon completion of her PhD, she was appointed as a lecturer at the University of the Witwatersrand in 1999, and in 2000, she was appointed at RAU as senior lecturer and continued carving out her niche in the fields of magnetism and magnetic materials. During her career, she attracted several research grants, including a UNESCO travel grant in 2002 to present work at a conference in the USA. She also received a travel grant to go to UBO in France, and an APS international travel grant awarded for her to visit the University of California, San Diego in 2010. In addition, she obtained various NRF research grants, all of them listed in the information you have in front of you. Professor Prinsloo and Dr. Shepherd also received an NNEP NRF infrastructure funding instruments grant to the value of 15 million rand to purchase a cryogenic physical properties measurement system. During Prof. Prinsloo's career, she worked as a visiting scientist at a number of research centers, including IBM Almaden Research Center in the USA, also UBO Magnetism Lab in France in 2005, Hitachi Almaden Research Group in the USA in 2006, and the University of California Center for Magnetic Recording, also in the United States. She also did an additional time period at UBO Labs in 2014. In addition, she participated in specialized measurements at a number of institutions, including Nexa in South Africa, ANSTO in Australia, and Elettra in Italy. Prof. Prinsloo has supervised and co-supervised 3 masters and 6 PhD students to completions, as well as trained 3 postdoctoral research fellows. Several of these students and fellows received awards for presentations made at conferences and workshops locally and abroad. She has co-authored a total of 51 peer-reviewed papers, most of these published in accredited journals with good impact factors, as well as 26 papers in peer-reviewed conference proceedings. Prof. Prinsloo acted as a reviewer for conference proceedings and accredited journals, as well as evaluated projects for international measurement facilities. In addition, she regularly acts as external examiner for master's dissertations and doctoral theses. She also served on panels and refereed applications for the NRF. With that, colleagues, I introduce you to Professor Aletta Prinsloo.
Okay, are you ready for a lecture? Okay, good evening. Thank you for the very kind introductions. It's so nice to have all of you here tonight. It's really a special evening for me. And I walk around a lot, so they gave me a separate mic because I couldn't promise that I can stand still. And as you can see, I will talk about 20 years of chromium-based research, and I hope you booked out your entire evening for this talk. Now, when people hear you are a physicist, it might conjure up these global people that everyone knows. And if you're lucky, there's this one female, Marie Curie. Mostly, they just think of those weirdos in the Big Bang Theory. It's like, oh, so you're a physicist. Are you as weird as they are? Yes, I am. And I associate with Leonard, because Leonard is an experimentalist, and he loves his work, mostly. And the one big difference is that although Leonard always knew he wanted to be a physicist, I stumbled upon this career quite by accident. I was a little like Alice in Wonderland, wondering which road will I take. And if you don't know where you're going, any road will get you there. And who would have guessed that my road would end here? I was trained by wise men, and I think even my respondent can't believe I ended here, because in my third year, I put up this little joke in the entrance hall, together with an expression of my passion for physics. Needless to say, the then HOD, who you would recognize, called me in and made me sit on a very low chair in his office while explaining to me that physics is beautiful and we should love physics. And apparently that worked, mostly because he offered me a really good bursary for honors. And I wanted to become a chemist, and this bursary sort of was just the answer to any prayer. So who mind? I mean, I will still be on campus, I can socialize with my friends that's in chemistry, and I will have money. And this man also then introduced me to the wonders of chromium. Now, all of you have seen chromium everywhere. It's everywhere in your everyday life. There's the taps, the handles, the cars. And to beautify objects, we put it on guitars as well, just because it's pretty. Chromium has been pretty for ages. The Greeks thought that chromium was really special because when they worked with chromium and they mixed it with any other element, it was a dye. And that dye would change color depending on which element you added. So the word chromium comes from the Greek word chroma, that means color. It is a highly non-corrosive material, and that's why you see it on the taps. And then on places where you don't see it, and I don't think you want to see it, in hip replacements and knee replacements in bulk form. And then in hard disk drives, in data storage, and if you go down to nanoparticle form, you can find it in clean water systems and also in pharmaceutical materials. So chromium is a wonderful, wonderful material. And how does it happen that one material can be so lovely? Now, all things happen for a reason, and that reason is mostly physics. So tonight, this was the interesting part. Tonight, I will tell you about chromium and the physics related to that. True to my nature, please, I will not feel offended if you play on your phone, stare around, just don't bother the students next to you, okay? They might want to pay attention. Now, before I can tell you about the wonderful properties of chromium, we need to talk about magnetism, because all the wonderful properties of chromium comes from its magnetic properties. And the magnetic properties come from the spins of the electrons. So first, you've got the spin of the electron around the nucleus, and then its spin around its own axis. And a combination of these give materials their characteristics. The four magnetic properties that I will refer to constantly is ferromagnetism, antiferromagnetism, ferrimagnetism, and paramagnetism. What do you need to know? Firstly, ferro reminds you of ferrous, which is iron, and there the spins are all aligned in the same direction. Antiferromagnetism, the spins are up and down. Ferrimagnetism, the spins are up and down, but not equal in size. And for paramagnetism, the spins are random. These properties hold in a specific temperature region. And as you heat these materials, the spins get thermal energy and they can start to fluctuate. And you have a thermal fluctuation that causes a transition. If you look at ferromagnetic and ferrimagnetic, that transition is called the Curie temperature. While for antiferromagnetism, it's the Néel temperature. And as you heat, you go from these phases to the paramagnetic phase. Okay, now I can sense people are sleeping. And we've just started. There's a whole evening ahead. Now, chromium is element number 24, and it is body-centered cubic. What does that mean? It means that when you pack the atoms of chromium, it packs in a structure that's cubic, with atoms at the corners and an atom in the body center. Then you can repeat this through space. This is simple cubic, but imagine little balls there. You can repeat it through space, and you can get a crystal. Now, normally, these crystals are like random, but it can also be that you spend a lot of time, and you heat the material very slowly, and you pack perfect little crystals, which is a single crystal. Now, you must remember this. There will be questions. The electronic configuration of chromium is special, and it does not adhere to the normal packing of the electrons. So it does not adhere to the Aufbau principle, if you know what that is. It's not normal, like physicists. Then you can see, there we've got 6 electrons. So the electron to atom ratio, which I will just call E over A, for chromium is 6. Below the Néel temperature, we've got antiferromagnetism, and the Néel temperature is at 311, and above it, we have paramagnetism. Now, the magnetic properties originates in the formation of a spin density wave that forms when you cool down from the paramagnetic range down into the antiferromagnetic range. And then I found these beautiful pictures, and it looks really impressive. You can see there, chromium has an electron and hole Fermi surface, and as you cool down, they are mapped on top of each other, or they nest, and parts of these surfaces are destroyed. This beautiful, colorful image is 3D. This is 2D. To simplify it more, we've got black and white images. There's the electron and hole Fermi surfaces. You notice that the electron Fermi surface is smaller than the hole Fermi surface. As you cool down, and they map through the Q vector, they end up on top of each other. And in this region, the electron and holes recombine, and those parts of the Fermi surface are destroyed. You're only left with these little bits there. And through an interaction, an antiferromagnetic spin density wave is set up. Now visualize this. When you have current, and there's little resistance, then you have a very nice flow of current. If you now start taking away those particles that contribute to the current carrying, then what you will find is you will increase the resistance. As you go down in temperature, you would expect a normal metal to behave like this, a straight line. But in chromium, because current carriers are destroyed, not destroyed, they recombine in electron hole pairs, you get this increase in the resistance just below the Néel temperature. So the formation of the spin density wave leads to a change in the physical properties. And I show you resistivity or resistance because it's the easiest one. And it's also seen in all the other physical properties. How does this spin density wave look? Oh, before we do that, when we look at these particles, the spins, what we see is at very low temperatures, they are antiferromagnetically ordered. As you increase the temperature, they get thermally excited, and finally, as you go through the Néel transition, they are ordered randomly. So antiferromagnetic behavior here, and then through thermal fluctuations, you get to a paramagnetic phase. How does the spin density wave look? It is literally a wave that consists of spins. So if you look at the structure, it will be a sinusoidal wave. And the spins at the corner atoms will be up, while the spins at the center atoms will be down. Antiferromagnetic, up and down. It is a wave. Oops. So it varies sinusoidally through the lattice, and it takes 21 lattice spacings to complete one full wave. As you cool down, initially the spins are perpendicular to the Q vector, and then these spins flip at the very creative name of the transition, the spin flip temperature, and they are parallel to S. This happens at 112 kelvins. However, we obviously can't just study chromium because it's been studied a lot. So we need to add stuff, guys. And sometimes, if you add stuff, other elements, to the chromium, you can get a commensurate spin density wave phase. In these cases, the spin density wave is out of phase with the lattice. It's therefore incommensurate. If the spin density wave is commensurate with the lattice, we refer to it as the commensurate spin density wave phase. Now, where will I start? I mean, the Greeks knew that if they add elements, it will change the color. Where can I start? Well, I can start by explaining a very simple two-band model by looking at, first of all, the chromium, an element directly to its left. So it will have an E over A of 5. Or an element directly to the right. That will be an E over A of 7. Or we can even just add molybdenum that has exactly the same E over A value. And you can add anything to chromium. You are guaranteed there will be a change. Doesn't that make research easy? It's like, let's add anything. Okay, it's not that easy because in order for us to understand this, let's just start with chrome vanadium. If we add vanadium, it is electron poor. So this electron Fermi surface is actually becoming smaller, thus destabilizing the antiferromagnetism in this material and resulting in a decrease in the Néel temperature as we increase the concentration of vanadium. It is simple. You guys would agree. Now, if I add manganese, I've got an E over A of 7. And having an E over A of 7, it means that this electron surface will become bigger. Thus, there's a better fit. I stabilize the antiferromagnetic phase, and we increase the Néel temperature. And in addition, we now have a new phase, a commensurate phase that we don't see in pure chromium. And together with that, what I will talk about a lot is a triple point where the paramagnetic, commensurate, and incommensurate phases coexist. So you would agree chromium is simple. We know what we're doing. We can continue. Any questions? Everyone fine? Okay. Now, I've shown you chrome vanadium. You know that it decreases the Néel temperature, and chrome molybdenum also causes a decrease in the Néel temperature. How can that be? Because E over A remained the same. This works through a different mechanism than the very simple two-band model and its electron-hole pair breaking that occurs. Now, we are very fond of vanadium, molybdenum, and manganese. You would see this reoccur constantly. So I hope you paid attention, because otherwise the next 2 hours will be very long. Now, I started my research on chromium by looking at chrome silicon and chrome gallium single crystals. And Prof. Alberts was my supervisor, and Piet Smit was my co-supervisor. And I was thinking, what will I tell you? Because just reading this one sentence to Charles in the lab was like, there's 5 words that even I don't know anymore. So let's keep it simple. First of all, we got a nice phase diagram. And what we expect is that gallium will just suppress the Néel temperature. But no, we get a sudden increase and a triple point with a commensurate phase. And then we also did pressure work, and I hope that it's clear that there's some mirror image, and then you can fit all kinds of nice theories and make up a big, huge document that can be examined. For the chrome silicon, we see it's unique because the incommensurate to paramagnetic phase transition occurs at higher temperatures than the commensurate paramagnetic phase transition, which is unexpected because commensurate is better and more stable. So furthermore, let's look at the triple point. Obviously, the people that measured made a few mistakes, and there's a few lines that went wrong. So we had to re-look at this and make sure that things were right. For the rest, there is the one sentence, acoustic mode, vibrational anharmonicity. I mean, I didn't know how to venture out to try and explain this. But what I do want to explain is that my very first article was in PhysRef B. Not because I was so good. So Prof. Alberts was like, where do you want to publish? And I was standing there, which journal, which journal? PhysRef B, Prof. And Prof. Alberts was reluctant. He was like looking at me weirdly. I was like, I don't know if the work will be accepted. Only later did I realize that actually some journals are better than other journals. And this is a very difficult journal to get into. But of course, Prof. Alberts knew what he was doing, and we got this paper and many others accepted. Now, what did I learn? Well, Prof. Alberts and Piet taught me everything I know about chromium, and that's wonderful. They also told me how to write properly and how to be a responsible scientist, which I wasn't. So he made a huge success of that one. The one thing that I did learn is there's things that we believe must be. And there's things that we believe just can't be. It just can't be. And then you measure it, and as an experimental scientist, what you find is what is real. And I promise you, although it's only chromium, it still surprises me every day. Now, that's me. Okay. In case you're wondering why I'm showing weird people, that's Prof. Alberts. You will recognize him. He looks the same. And Piet, I haven't seen in years, so I can't vouch for Piet. But you see how young and fresh and happy I look. Okay. Then this happened. I graduated, and Prof. Alberts said, and now you will train your own students. And the very first student I had to train was Laudia. And I knew Laudia because I worked for Laudia at Vista. And I worked for Laudia because he appointed me while this person, that's Hartmut. Hartmut was on study leave. He wouldn't have appointed me. Where's Hartmut? Okay, he wouldn't have appointed me, but Laudia did. And then suddenly, I was Laudia's co-supervisor on chrome aluminium and chrome rhenium. Now, why chrome aluminium? I think you've got the drift now. What are we looking for? Some weird stuff to start off with. Now, aluminium, E/A of 3, and you can see we expect this decrease, but voila. There's an increase, unexpected. So that two-band model works for like 2 materials. The rest, it's all exceptions. And then lots of debate there around the triple point, where should it really be? And there at the high concentrations, very unique characteristics. We are looking there at antiferromagnetism together with semiconductor properties. Wonderful system to study. I just can't get enough of it. We revisit it constantly. And chrome rhenium, that's chromium with a group 8 impurity. We just can't get enough of that. We keep on getting back to these chromiums with group 8. You will see Susan then did a PhD on chrome rhenium again. Nice paper, but I didn't try to explain anything. Then I met this wonderful person, really friendly on a right there, Andrew. Andrew was at Nexa. And as I was working at Vista, and I was struggling to finish writing up, Prof. Alberts was desperate to get me out and get this degree. He said I cannot measure in his labs. But I had a solution. Andrew didn't know I couldn't measure. So I took my samples from my PhD and I phoned Andrew. I was like, Andrew, can I come and do experiments? And I hardly knew Andrew, but I was desperate to get to a lab. And Andrew said yes. There's Andrew at the beamline. And that was a wonderful few weeks I spent at Nexa not writing up. But then Prof. Alberts finally heard about it. So I really made Nexa part of my world. And we did wonderful work together. We luckily did get a paper from the weeks I spent at Nexa. And this collaboration is ongoing. We still do neutron work together with Andrew. Now, why would you want to do neutron work? Because it's not good for you. I mean, all those neutrons, it's like X-rays, not good for you. And at that stage, they weren't as safe as they are now. But let's not talk about that. We want to find out exactly what phase are we in. And the only way to know that is to do neutron work. So if you go to a specific temperature and you sit there and you count and count and count through neutron diffraction, and you get a central peak with 2 satellites, you know you are in the incommensurate phase. If you only get a central peak, you are in the commensurate phase. Now, obviously, it's not as simple as that, because you then have to measure plenty of temperatures, work out the area underneath these curves, and then you can actually find out exactly where the phase transitions are. So in general, we can guess we're in the incommensurate phase by thinking about the two-band model, or in the commensurate phase. But the only way to know for sure is to do neutron work. And that is why Andrew is one of my best friends. I hope you know that, Andrew. Okay. And then I started more training of students. The pressure was much less then. We didn't have to produce 3 PhDs and 3 MScs in 1 year. They expected you to produce some students. And the first work was on chrome iron. And chrome iron looks very similar to chrome silicon if I look at the phase diagram. Again, incommensurate paramagnetic, higher temperatures than commensurate paramagnetic. So as I know about chrome silicon, we thought this would be a good choice for me to train a student on chrome iron. And that student was Helen. And Helen and her parents are here tonight. And she is now headmistress of her own private school, not doing any physics. Maybe with the students still, Helen? Yeah. And the next one was Roru. He's now a senior scientist at the CSIR, working on my other favorite, chrome gallium, and just adding manganese and vanadium and seeing what will happen, getting phase diagrams, there's plenty of phase diagrams, and then fitting theories to that phase diagram and writing papers about that. But then at some point, Prof. Alberts and I was getting really concerned because there was already so much work about the chromium out there. And what will I do? Because, you know, he was going to retire and he was worried about me. What will Aletta do? And he said I should start making plans and think about the future, which I was not very good with. But then there was quantum phase transitions that came to the foreground in literature, and quantum critical points. So a quantum phase transition occurs at 0 Kelvin. And at that point, we will have a quantum critical point. When we looked at the conventional phase transitions, it was related to thermal excitations. So there was thermal fluctuations of the spins, and then finally, we could move into the paramagnetic phase. But in this case, the transition would be due to quantum fluctuations, and it will happen at 0 Kelvin. Now, how will I make that happen? Well, you obviously have to do something to the sample. It will not sit there and voila, I've got this. What we need to do is we have to work with a tuning parameter. Tuning parameters can be pressure, field, or doping. And in that way, you can force the sample into a quantum phase transition. However, I was lucky enough to get a new group partner, and Charles became my chromium partner in crime. And we're still in one group, and we haven't killed each other. Things are going well, guys. So Charles started working with me and Prof. Alberts, and mostly in this initial phase, we started looking at quantum phase transitions. But will there be a quantum phase transition in chromium alloys? I mean, chromium is such a simple material. It's body-centered cubic. No big structures, no complex things to understand. It's a very, very simple material. So will there be quantum criticalities? And luckily for us, somebody else found out there was. And you could see that they used pressure as a tuning parameter to put this Néel transition, to pressurize this Néel transition down to 0. And this was chrome plus 3.2 atomic percent vanadium. And then you can do all kinds of fits to confirm it is a quantum phase transition. Then there were other people that used doping as a tuning parameter. And it went down, this is vanadium, adding vanadium. But now you can see, previously we thought this was just a straight line. But look what happens down there. There we've got a quantum phase transition. So we were really excited. However, we had a big problem because what we needed was low temperature, high fields, and pressure. And we didn't have that. We typically measured from 77 Kelvin, that was liquid nitrogen, upwards. And then once in 2 years, you will get this dewar of helium, and you will sit there the whole night and measure because it's so expensive. And you just have to get the measurements done before the helium is gone. But then these friendly people passed my way. That's Andre. He's here tonight. Andre was working on really complex systems, not body-centered cubic systems. Complex systems with low phase transitions, and he needed fields, and he was publishing a lot. And Kinta, who was then the dean, supported the application for funding, and he got us a quantum design PPMS measurement apparatus, which gave me a lot of PMS, but that's a whole other story that we will not address tonight. But thankfully, Andre got this apparatus, and we could measure on his apparatus, and we were very excited. What will we measure? The first obvious choice was for us the group 8s. The group 8 elements with chromium has this phase diagram that shows first an increase in the transition temperature as expected as you increase this electron surface, and finally, obviously, the electron surface becomes bigger than the whole surface and it destabilizes. So that is optimum nesting, and then it turns around. So we were sitting thinking that if we can start here, maybe we can measure something. But our fields weren't high enough, our pressures weren't high enough, so we doped. And we worked on chrome, ruthenium, vanadium, starting here at 14%, adding vanadium. That was our very first choice. And you wouldn't believe it, we got a sucker to do that experiment for us. Yeah, I was so blessed when Krish came in and he wanted to do a PhD, because I was thinking how I would sit there doing all these measurements. But then we got this PhD student and he was ambitious and we were thankful. And you won't believe it, we did get quantum critical behavior. There we can see the Néel temperature pushed to 0, the relative change in the resistance down to 0. Then the Hall coefficient shows a step-like behavior, and an anomaly in the Sommerfeld coefficient. And if you are still awake and wondering what is the Sommerfeld coefficient or the Hall coefficient, it really doesn't matter in your life. The only thing you need to know is we need to measure a lot of samples and do a lot of measurements before we can actually say that we have a quantum phase transition. Just for people that give funding, each one of those little points is a sample, and each sample costs around 1,500 rands to make. And it takes 2 weeks to make your sample, then you have to X-ray it, do electron microprobe, and decide if it's good enough to continue. And then there's weeks, days, months of measuring. And the best paper, I think, from this work is the one where we showed that the Seebeck coefficient, or the thermal power, is a decisive parameter if we look at quantum phase transitions in chromium alloys. Because before that, there was no evidence for the thermal power to indicate quantum phase transitions until we wrote this paper together with Andre, because he knew about heavy fermion systems. And that was already proven for heavy fermion systems. And while we were on a roll, I was hoping to get this cookie cutter research out there, because now I know about quantum phase transitions, and we can just dope, and we can publish. But now it's not that simple. However, we did continue. This is Blessed Mchunu. He was on sabbatical from NUST, that's in Zimbabwe, and his master's dissertation is the only one to date that has been upgraded to a PhD in the physics department by an outside panel. His work on chrome aluminium with molybdenum and vanadium focused again on this triple point. You would see previously Smith and Alberts worked on chrome aluminium molybdenum, and they could suppress the transitions here. But there is the problem. We couldn't measure at low temperatures. Thus, we couldn't determine whether it was a quantum phase transition. Now, with the quantum design apparatus, we could actually do that. And surprise, there was a quantum critical point. This was a very nice PhD. We had several conference presentations, conference papers, and then a lot of journal publications, even one as recently as this year. That's several years after him completing his PhD. Now, if chrome aluminium vanadium was that great, why don't we just do chrome aluminium again? It's like a circle, we just can't get enough of chrome aluminium. And just looking at pure chrome aluminium, we found that looking at all the measurements that we could do now, there was a step in the Hall coefficient, an inflection in the Sommerfeld coefficient and a nice anomaly there in the Seebeck coefficient, which means that the phase line that was originally drawn for chrome aluminium was actually not correct, and that phase line is actually pointing towards 0, and that this IC transition is not a transition that's due to thermal excitations, but rather a transition that is due to quantum fluctuations, because you can see it impacts down to 0. Nice paper. That's just to show we did publish. Okay. We also revisited chrome silicon. And Charles added to this molybdenum, because the vanadium was suppressing the transitions way too quickly, but he only found that out the hard, real way by doing it, and then redoing it with molybdenum. So what we were hoping was to suppress this transition to a quantum criticality. But just look at the lovely results. Step, okay, we'll skip that. Look there. There we have a nice down to 0 line from the IC transition, and there we go from the commensurate to the paramagnetic phase. So we got 2 quantum critical points in the system. We of course promised to go back, but we haven't had time yet. And then Susan joined the group, and she worked again on chrome-rhenium, which was one of the things that Claudia worked on. I think maybe I'm lazy to read all the literature, so we just keep going back to the ones I know. And there we can see nice quantum critical point. But what is happening there? There's something weird happening in this system. It's not a nice straight line. And the Sommerfeld coefficient showed this huge minimum and then the quantum critical point at this side. After much debate and discussing it with wise people, we concluded that the addition of vanadium changes the original commensurate phase to an incommensurate phase. And when I was preparing this talk, so there was a good thing from this talk, look what we saw. There is a nice sharp line if we look at the susceptibility that we measured at UFSCar in Brazil, indicating that this is a quantum critical point, and it probably is evidence that we are going here from a commensurate to an incommensurate phase. And yes, Susan did get a degree this year. Yay! I'm proud of Susan. And we made Sassel part of our lives, and we reached new frontiers. We got Claudia, that was working at Sassel, to help us use high fields as a doping, as a tuning parameter. Here you can see we measured as function of field, and clearly this transition temperature changes. Many days, nights, measurements later, we have this nice curve that shows how Tn changes with field, but no quantum critical point. And we were a little bit desperate, but luckily Susan did read articles, and we saw this paper of Jaramello that showed when they used pressure as a tuning parameter, they also got this exponential decay. This is a very pretty picture. The following article does not have such a pretty picture, but they finally showed that you can push this down to a quantum critical point. But you need really low temperatures and really high fields. And at that stage, there was this big blessing. A miracle occurred. I convinced the dean, that was then the dean, to support a funding initiative from Charles and myself, and we got this beautiful apparatus. Look, smiling, happy. This apparatus is actually green, and we call it Shrek. And Shrek is big and green. And Shrek can measure from 50 millikelvins to 1,200 kelvins, and fields up to 14 Tesla. Okay, this is really a difficult machine to work, but Charles immediately climbed in. And we measured everything we could because we need to get to know the apparatus. And the work of Rodney on chrome osmium was most interesting, because there you see the normal resistance, and there's the increase when the spin density wave forms. The other sample is just a paramagnetic sample. But when you looked at the load, when you looked there and you zoomed in, you could see a downturn. And when we measured that sample, we could see a clear step. And this step goes to 0 in the resistance. So we finally found superconductivity in the samples, and we've been chasing it for years. So thanks to our cryogenic apparatus, we finally could measure it. And now we are at phase diagram for chrome osmium with a commensurate, paramagnetic, and superconducting phase, reminiscent of really complex systems that showed a superconducting dome. That just left us thinking that we should revisit all the samples we've ever measured. But of course, there's no time, and each measurement takes a lot of time. But this is proof that antiferromagnetism can coexist with superconductivity in the same sample, and then that chromium alloys, although they are simple materials, does have very unique properties. And if you are still awake, we're just halfway now, but bear with me. So what more can we do? We want to revisit all these samples, but chromium is so diverse. What can we look at that will help us grow as a chromium group? And the thing we could look at was thin films. So now, instead of having a bulk sample, and a bulk sample is not a bulk sample, it's a bulk sample. So instead of having a bulk sample, we wanted to look at a substrate and then put on top of that a thin layer of chromium material. Once you do that, you change the properties of that alloy, and you change it due to the dimensions or the dimensionality that changes. Now, why would we want to do that? Because substrates are really expensive. We want to do that because thin films and structures consisting of thin films make up so much of the modern technologies that you find in data storage and sensors. So venturing in that field, we can also look at some applications on the long term. And where do you start if you want to start something completely new? Well, you start by finding somebody that can already do it. And I found somebody. Prof. Alberts knew Eric Fullerton. He was invited for a conference, and I made him a best friend very quickly because this guy knew about thin films. Eric Fullerton was at that stage at IBM and then moved to Hitachi, and then at present he is at University of California, San Diego. Very prominent scientist, very, very good with thin films. So that was one good connection. I visited him several times. Charles also visited him. And then there was the arranged marriage. I had an arranged marriage with David Decker-Jevy from UBO. And that marriage is still lasting. You won't believe it. So why an arranged marriage? Because the original agreement would have been between Prof. Alberts and Prof. Legault, but they wanted to retire. So we got the agreement, and it worked out well. So this arranged marriage is still functional and working extremely well. The first films we made was chrome ruthenium, and these pictures are atomic force microscopy images. And as you change the thickness, you can see how the little crystals change. And in the last image, you can actually see nice little cubes. And if they're lighter, they are higher. So it's little pillars that grows on your substrate. We showed that depending on the growth morphology, you will get different Néel temperatures. When I went to IBM, they made me sign a contract, and I was always wondering about this, because that same year, they actually introduced pixie dust to their data storage units. And pixie dust is a thin layer of ruthenium that they add to the chromium layer. And in adding that, they increased their capacity for writing 4 times. Chrome aluminium in thin films. And there's patience, she got a degree. Again, we looked at atomic force microscopy. And what we also looked at is stress and strain in the films, together with Andrew at Nexa, that has specialized XOD equipment. And we showed that the smaller the particle, the higher the stress. We looked at plenty of thin films, but I want to show you the chrome cobalt because Charles spent days making those diagrams. So all of you must behold the lovely 3D figures. There you can see the resistance changing. There's the Néel temperature for different concentrations. And then there is the values at 2 Kelvin. So I think we need 3D images. And Charles produced 3D images for us. Looking at everything we can possibly measure, you would agree that there's clear correspondence at a specific point, which is actually the new triple point. The triple point there is now lower and at a different concentration than the bulk material. Maria she's like, okay. That was a clear indication that I should talk faster. And this point is now at a different point. And at that point where we have the optimum overlap, we thought that would be the point where the system is the most stable. But no, it's not. The system remains the most stable at the triple point, which we still firmly believe must be a quantum critical point. Even the distance between the atoms in the structure, which I didn't show the plot of, is optimal at that position, and not at the point where you've got the best overlap between the surfaces. Then we decided the next step would be to confine the spin density wave between other layers. This is the famous experiment by Fert and Grunberg that won them the Nobel Prize in 2007. There's the iron, and they align in the same direction. And the spin density wave of the chrome in between, varying with nodes. Look at the nodes there, where the spins are the same. So firstly, the iron wants to align in a ferromagnetic order. The chrome wants to align anti-ferromagnetically. So this spin must be opposite to that one, and you must have the maximum amplitude at the interface. But of course, we cannot just do what the others did, so we decided to add a layer that is commensurate. So chrome manganese. So we have chrome manganese, chromium, chrome manganese, chromium. And the chromium we varied in thickness. Doing some neutron diffraction work and fitting the Hendricks-Tauler approach to model the superlattice, we could get some constants, and then we could draw these nice images of spin density waves, where this is the chrome manganese and this is the chromium. Note the number of nodes changes as we increase the thickness. This proved the theory of Fishman was correct, but there was a little surprise because, let's go back there. If you had a specific thickness and you cool down, the number of nodes will change from 0 to 1, 2, 3, 4, 5. And this is exactly what we saw. As we cooled down, the number of nodes increased, which was the theory of Fishman. But we also found a little surprise, that when you heat it, the number of nodes from 4 to 5 and 5 to 4 changed at different temperatures. So there was clear hysteresis that can also be seen in the resistance graphs. And this happens because the one chrome-manganese layer must get enough energy to flip around before we can continue to the next number of nodes. Just to prove, we did publish with our collaborators. There's just a few of the articles with, firstly, Eric, and this is with UBO. Both collaborations are ongoing and very fruitful. But the obvious next step, and we're now 2/3 through the talk, be strong. The next obvious step was to go from bulk to thin films and now to nano. And we decided to go for nano because chromite nanoparticles have very nice physics. So the physics include magnetic frustration, spiral ordering, and multiferrocity. If you still don't know what it's about, you should read more. It's unacceptable. Okay, and you can apply this in the medical fields. And what we were hoping is that we can tailor the properties of the chromites by adding other materials. Now, the first time we encountered nanoparticles was with our collaborators at UBO, and that is Jerome Ritchie. And Jerome Ritchie was a PhD student that originally registered at UBO with David, but then we decided to do a joint degree because we had apparatus here that he could use. They produced whatever they wanted there. He came here for months on end and did measurements. And he got a UJ-UBO joint degree. And that's our very first paper on nanoparticles. Charles and I debated, what will we do? Because we really wanted to work on chromites, but we had this vision for the group to grow into something modern, into something new. Not leaving behind the bulk and the thin films, but adding things that will be highly appropriate for 4IR. I had to say that, guys. Okay. And luckily, Pankaj Mohanty, Pankaj, where's you? Where you? There's Pankaj. Pankaj joined our group. He applied to be a postdoctoral fellow, and late in 2015, he joined the group and immediately started making particles. Note, I didn't call them nanoparticles. But we published, we had conferences, we had conference proceedings, and Pankaj won the most prizes I've ever seen from any postdoctoral research fellow. Well done, Pankaj, we're proud of you as well. And we finally had a nice, big, good paper there. The only problem was, the nice big paper was on microparticles, not nanoparticles. But nevertheless, beautiful TEM images showing bipyramidal shapes with flattened ends there. Then we got Farai Rubengu that came from Zimbabwe. And Charles said, look, we need to be better in the lab. We need to check the temperatures. We need this, we need that. And Farai could do this. And we finally got nanoparticles. So I'm happy to say we now produce nanoparticles within the Chromium group at UJ APK campus. However, I must warn you that the chromites are not as simple as bulk chrome. You can still see a cube there, can you? Great, there were still people awake. But inside the cube, there's some octahedrals and tetrahedrals, and this is then the B site and the A site that people refer to. And as we are the Chromium group, Chromium needs to feature. So whenever I get an application, I just tell them, Chromium needs to feature. And Chromium features there. So Pankaj started this nanoparticle, microparticle thing, and we are going strong now. This is a figure of a normal spinel structure because chromites are spinels. And this was generated using Vesta software. So it's perfect, but nothing is perfect. Remember, things are real. It's not as you imagine. And changing the first material, there we've got nickel chromite. This is another publication. You can see that the tetrahedrals are elongated. if you now start adding copper into that site, you can flatten them. So by doping, you can actually change the structure. And in addition to that, my favorite, you can change the magnetism. These are neutron images that Andrew helped us with. And you can see if you start with nickel chromite and you add cobalt, you can change the transition temperature. Thus, you can tailor it for whatever property you want. You can even add phases. There's copper nickel chromite. Initially, you only have this ferromagnetic to paramagnetic transition, but by keep on adding nickel into the copper sites, you can also add in an antiferromagnetic phase. Okay, there you see it, a nice phase diagram, my favorite, where you've got ferromagnetic to paramagnetic, and then you've added in a nil temperature. So by playing around with the various dopants, you can change the structure and you can change the magnetic properties. And now I will show you a cartoon. You can wake up, stop playing on your phone. If you paid attention, which maybe 2% did, you would agree that Greek philosophers had a big question. And that question was, of course the elements are earth, water, fire, and air. But what about chromium? Surely you can't ignore chromium. Are you convinced about that? You must say yes, otherwise I go back. Okay, you agree. Great. So I hope I've convinced you that chromium and chromium compounds, that's chromites, chromium in bulk, chromium in thin film, chromes in nanoparticles, are the most wonderful material, and all of you now want to study that. I also hope that I've convinced the Dean and the MEC representative that the research to date has contributed to the UJGES, and that our future research is highly relevant to the fourth industrial revolution, because there's lots of applications in the medical field and data storage. The chromium group today looks like this, and there's some young, fresh, happy faces. Charles and me getting older. Okay, but soon they will also start looking like us. I just want to say that all four of us are thinking about future research. But I want to tell everyone here what Marie Curie said, and I think we as scientists should live by this and not continually try and run after producing something. She said, on radium, the work was one of pure science, and this is proof that the scientific work must not be considered from the point of view of direct usefulness. It must be done for itself. It must be done for the beauty of science, and then maybe humanity can benefit from it. So we must strive to understand the fundamentals instead of just striving to produce. All that said, we've got lots of plans for the future. I don't know if I want to go through all of that, but we're still going to do magnetic phase diagrams. We're going to look at quantum criticalities, at superconductivity, and we're also going to see if in bulk material we can have materials that can have applications where it does not expand with temperature. So INVAR and L-INVAR characteristics. We're going to look at thin films to see the beauty of the spin density wave and how it's influenced by dimensionality. But we're also going to think about how can we apply this in data storage. We want to keep the links with industry and try and see if we can apply what we are doing, but we want to do it for the beauty of science. We're also going to look at nanoparticles, and once we've got perfect nanoparticles, we hope to make core shell particles, which can find application in biomedical fields or water purification. But I do believe strongly, from my point of view, we must strive to do the best science we can, and not to produce the best product. Now, there's a nice cartoon, you can wake up again. After listening to me, even SpongeBob knows that everything's chrome in the future. I hope you are also convinced. To every colleague, to every family member, to every one of my physics family that's here tonight, thank you so much. Special thank you for Prof. Alberts, because he agreed to be my respondent, and for Charles for supporting the research so well. And then to these people, a huge, huge, huge thank you. Okay, that was me. Thank you, guys.
So what shall I say after this well-presented talk? Professor Swart, Professor Meyer, Professor Prinsloo, ladies and gentlemen, I gladly respond to Professor Prinsloo's inaugural lecture. My second paragraph was about applications of what one can do with all these things. I think that must be pursued. See whether there will be practical applications for everything. Professor Prinsloo clearly pointed out the unique density wave antiferromagnetic properties of chromium and its alloys. The role of the nesting of the electron and hole Fermi surface sheets on almost all of its physical properties was emphasized. Properties like the electrical resistivity, thermal expansion, magnetic susceptibility, specific heat, thermoelectric power, elastic constants, indeed a remarkable metal and its alloys with extraordinary and large magnetic contributions to all its physical properties. Every time in the past that one thought research in chromium and its alloys had reached its peak, one is surprised by new aspects that pop up, giving new life for research on these materials. The most recent example in this case is Professor Prinsloo's work and the research group on entering into new exciting research fields with chromium and its alloys. Fields like thin films, she mentioned a lot of them, magnetic multilayers, nanostructures, quantum criticality, superconductivity, semiconductivity and spin glasses, behavior, chromites, etc. Indeed, a very long list of new research fields and possible new applications. There should be applications. Even possible uses in the medical and water purification fields. The group's collaboration with, in this regard, with Professor Fullerton and Dr. Decajevi of France, both outstanding researchers, is long-standing. To my mind, it emphasizes Professor Prinsloo and the group's high standing on the international level. The Chromium project is running in the department continually now for several decades. Under Professor Prinsloo's leadership, the Chromium Research Group produced MSc and PhD students of the highest quality, as well as exciting research papers in highly rated international journals. The group is excellently equipped for all their planned new programs. This includes, for example, the group's most modern cryogenic measuring system for studies at extreme conditions of temperature and magnetic fields. Professor Prinsloo mentioned that. We needed facilities at the co-workers' laboratories are also available. I therefore have no doubt that the groups entering into the new research fields, measured in their presentation, will lead to a new era for chromium and its alloys, in which Professor Prinsloo and the group will definitely play a significant role. Ladies and gentlemen, please allow me to close on a personal note. Professor Prinsloo, I am very proud of you and your group's achievements. I wish you, Dr. Shepherd, and the group many successful years in your future research on this wonderful metal, chromium and its alloys. I also honor your family for their role in your success, because I know they have a big role in your success. I won't be long on this chair. I thank you.
So, ladies and gentlemen, you would have noted that our inductee tonight's the only one sitting in this row without a gown. So the process now will be that for recognition of the hard work that's been done together with this achievement of a professor, full professor, for this wonderful presentation now, we're going to rope her accordingly and welcome her to the cohort of full professors in the University of Johannesburg and internationally. Can I ask everybody to join me, please?
Okay, guys, take pictures. The dean is going to dress me. Emma, are you ready for this?
So, ladies and gentlemen, I know you're very keen to join us where we started earlier, but just allow me a few minutes to make a few concluding remarks. And I made a number of notes here as Professor Prinsloo were talking, but I'm going to go away from that, and I just want to make two remarks regarding the presentation, Professor. Is the first one that many people say that as we move up the hierarchy to become full professors and we do more and more research, we'll use that tact to become a good facilitator of learning, a good teacher. And I think she's proven that completely wrong tonight. What a great facilitator of learning. And then secondly, but I know you people in science don't watch TV because the dean's always saying, write journals, journals, journals. So you'll know there's an event currently on TV, because it's also Women's Month, that says that they've looked at the number of powerful women and say, describe yourself with one word, and just look at it. And I was just reflecting on that, and I looked at the words such as powerful, exciting, knowledgeable, sense of humor, that's very important, good vision for the future, but also very articulate. And I've summarized that all to say you are really a great scholar. We're very happy to have you at the University of Johannesburg. Well done tonight. Let's give her a round of applause. Professor Albert, thank you very much for acting as a respondent and visiting the university again. I think the comments that you've made about the application that has to be developed is a very valid point. It also came through in the presentation. But also the new opportunities to link with other domains, such as the medical domain. It talks a lot to where we want to go. And obviously, I think the colleague has made it very clear I must communicate over that the 4IR has presented here. I will communicate the message accordingly and take it forward. But also allow me on behalf of the university management and everybody in the university to also, as Professor Albert has also done, to extend a warm word of appreciation and value from the university for the contribution of family members towards this great achievement. We know those achievements don't come easy, and it's not easy to achieve without sacrifices at home, lots of time, weekend work, traveling, and a range of other issues. So let's also give the family members a round of applause for their contribution. And then just to the faculty, Professor Meyer, the Vice Deans, both the Vice Deans are present here, other leaders in the faculty, thank you very much for creating an environment where scholars such as this can flourish and share their knowledge with us. It's much appreciated. Ladies and gentlemen, Professor Prinsloo will be, as we leave now, will be waiting at the exit here where we can share a personal word of congratulations with her. Refreshments will be joined where we were celebrating earlier, where we get to know each other. May I please ask you to rise as the procession leaves the venue. Thank you very much for your presence.